Up until now, we've been talking about things like differences and associations and correlations, but we haven't been talking about whether those differences or associations or correlations are statistically significant. And that's a term that you certainly hear from time to time. And I want to take a moment to talk about what that is and what it means. But to do that, we need to understand what two other terms mean first. One of them is population, and the other one is sample. The population is every element in the set of things that we're interested in. So, for example, if we were trying to understand New Zealand voters, then the population would be every single person who's registered to vote. And we might want to take a sample of those, maybe 1,000 voters or something like that, to try to then extrapolate to the population. So we're looking at the sample, and based on what we learn from the sample, we're trying to apply it to the population to make a prediction about them. For example, what party is going to win an election or something like that. When we talk about statistical significance, what we mean is the probability that what we learn from the sample is true for the general population. So when we say a result is statistically significant, what it means is it's extremely unlikely that the inference we made about the population based on the results that we got from a sample is incorrect because there's something strange about the sample that we drew. The sample is somehow atypical. Anytime that we're talking about statistical significance, it's important to recognize that we're making an assumption, and lots of statistical techniques are based on this. And that's that each element within the population has a known non-zero chance of inclusion in the sample. There's a bunch of different sampling methods, and we won't go into them now. But the key thing about this assumption is that everybody does have to have a chance to be included in the sample. Otherwise, the chances that that sample is somehow incorrect or wrong or atypical increases. In reality, that actually happens a lot. For if you think about any opt-in survey, for example, then people who choose not to participate have a zero chance of being included because they're just going to refuse. Similarly, if we were doing a survey of likely voters and we were only calling landlines, then everybody who only uses a mobile phone would be excluded. Even though that's true, we often still apply the same statistical techniques, but the more this assumption is violated, then the more that we need to question whether some of those statistical techniques are correct, or at least take the idea of statistical significance with a grain of salt because we know we haven't satisfied this important assumption. But assuming that we have, or we've gotten close in terms of being able to draw a good sample in which at least most elements of the population did have a chance of being included, when does statistical significance matter? To do that, we need to think about when we actually are working with the full population versus just a sample. It used to be that we were almost always just working with a sample because it was just too expensive and cumbersome to work with the whole population. The one big exception was the census, where they did try to talk to everybody. They did try to reach the whole population. But for many surveys and things like that, likely voters are a good example. Also, a lot of corporate market research, people would just talk to a sample and try to extrapolate to the population. This has changed a bit recently with the advent of sensors and big data and things like that, because now sometimes we can actually see the whole population. For example, if we're a telecommunications company like telecom, we can see the activity of all of our customers. We could conceivably look at the whole population and look at the data for all of them. We wouldn't need to just use a sample. Other examples like that are, for instance, if we are an app developer and we're looking at the data for all of our users, again, we can see the data from all the users. There's no reason to have to do a sample. Another example like that would be if we were a retailer, we can see the data from all of our customers without just having to choose a sample. Anytime that we're working with the entire population rather than just a sample, we don't really even need to think about statistical significance anymore because we're not trying to extrapolate from the sample to the population. In essence, what we're just doing is counting what's happening in the population. So then our result is just the result. There's no need to think about the notion of statistical significance. In the situations where we do have a sample and we're trying to extrapolate to the population, there's a few things to consider as we think about the notion of statistical significance. One of them is our sample size. If we have a big enough sample, it's easier to find statistically significant differences. So for instance, if we are looking for a difference between two groups, maybe we're trying to find out, is there a difference between men and women? If there's only a small difference, that will be harder to see in a small sample. We might need a bigger sample to be able to see that difference. That magnitude of that difference is called effect size. And these two things kind of work together in the sense that the bigger the effect size, the smaller the sample we need to see it. Conversely, the smaller the effect size, the bigger the sample we need. So what I mean by effect size is things like the difference. So if, for instance, it was a difference between men and women, if there's a big difference between them, we can see it with a small sample. If there's only a small difference between them, then we're going to need a bigger sample to be confident that that difference is really there. So that is kind of the more technical things to look at when we talk about statistical significance, but it's also really important to consider the consequences of being wrong. So in one of the areas where statistical significance is really important are things like drug trials, because we don't want to conclude, for instance, that a drug is safe when it isn't. Our consequences of being wrong might be really high because there might be really bad side effects or people might actually die. So in those cases, we're going to rely on statistical significance and we're going to want a really high standard of statistical significance before accepting that something is true. In many organizational settings, though, the consequences of being wrong aren't nearly as high. We're just trying to figure out something like, should we go with this strategy or that strategy? Or should we use this method of communication or that method of communication? One might be better than the other, but the consequences of getting it wrong aren't nearly as serious. So we wouldn't have to have as high of a standard of statistical significance as we might for some of those other more life and death things like drug trials or other safety related things. Another thing to think about too is statistically significant results versus meaningful results. As I mentioned before, if we have a big enough sample size, we can find statistically significant differences even if they're quite small. But from an operational level, those small differences might not make much of a difference. So for instance, if we saw that there was a difference between men and women, but the difference was tiny, there might not be much that we would do about that difference. It's not like we're going to treat men and women differently because the actual average level of difference between those two groups is so small that it doesn't actually matter. And again, this kind of thing can happen a lot in an organizational setting where we'll see some sort of an association or a difference, but it doesn't really practically make a difference in what we're actually going to do.